In the previous video, we wrote an equation based on the amplitude and frequency of different parts of our tone, of our note. And in this one, we're going to see what happens when we take that tone or note and we apply our effects to it. Now, to get started, I've created this DESMOS template, and you'll see a link in the video description, also in Teams. And you'll be able to manipulate this with your information so that you can model your effect and what it's doing to your sound. If you're going for the meeting level, we're going to take a single tone and modify it. That means a single frequency, no extra complexities, and modify that. Before I get in on the project, let me just remind you of what the different letters affect. So A is for amplitude. It affects the amplitude. Increase it, the waveform gets stronger. Decrease it, it gets weaker. B affects the period. Increase the period and you shrink the waveform, or increase the frequency. The frequency goes up as the B goes up. And if you shrink B, the waveform or the period expands. The frequency goes down, we get a lower note. C affects our phase shift. So as you shift it to the left, the graph goes to the right. And as you shift it to the right, the graph goes to the left. And lastly, D, which we're not going to actually use in our modeling because it's the example of, say, a speaker being in this position versus being a little bit closer. And without all the complexities of the room and everything else around it, it really doesn't mean anything for our application. But I did want to show you what D does. And if you increase D, it shifts the graph up. And if you decrease D, it shifts the graph down. But for our sakes, we're going to go ahead and leave it at 0. Okay, so the first thing you need to do is enter in the B from your fundamental, your lowest note from last week's modeling. For mine, that B was 5.587, and that's just to get our baseline frequency before we apply any effects to it. Go ahead and leave the amplitude at 1 because that's how we were leaving our fundamental harmonic, and leave C and D at 0 for now. Next, you're going to adjust A, B, or C based on what the effect is actually doing. We're going to try to model it. So if I had an effect that was going to make that certain tone louder or quieter, I would do something to affect the parameter A. If I wanted something that was going to make the pitch go higher and lower, I would do something that would affect the parameter B. And if I were to do something that would affect the phase shift, either a phase shifting effect or a delay or reverb that delays it in time or shifts it backwards in time, I would do something to affect parameter C. Now, in this model, if you look down below, you can see that I have a square wave, a sawtooth wave, and a triangle wave modeled, and they are all attached to the A, B, C, and D. So what I'm going to do now is go one by one. Amplitude, period, phase shift, and show you how different effects might affect these. I can't do every effect, and your effect might need my guidance and for us to work together to work it out. So first, amplitude. There's an effect called tremolo, which makes the volume go up and down in a cyclical pattern. Well, what do we know goes in a cyclical pattern, up and down? Well, that's what a sine wave does. So instead of A just being equal to 1, I can put A is equal to 1 times some sort of sine function. But if I just make it sine x, the volume would be increasing and decreasing so fast it would actually be an audible tone. For it to be a volume effect I hear, it's going to actually have to occur over many different cycles of that waveform. So I need to choose a much smaller B for my x in this A parameter. So if I pick like 0.01, okay, and you'll see right here the wiggles in the middle right now are really little. But if I sort of zoom back out, so I zoomed way out on my x's, but I kept my y's the same so I could see the amplitude change. And as you can see here, the amplitude goes up and then back down. And if I zoom in, these things that look like one giant waveform are actually made of multiple smaller waveforms. So you have the smaller waveforms as the tone I hear, but the larger waveform is the volume going up and back down and up and back down. So, okay, so now what if the frequency shifts up or down? Well, I can do a very similar thing. Instead of having 5.587, I can multiply times the sine. And again, this shifting effect isn't going to be super fast. It's going to happen over much longer periods of time. And so I want a smaller number like 0.01. Okay, the added complexity here with shifting the frequency is that I don't want to multiply by a number that swings around 0, because if I multiply my frequency by 0, that doesn't make any sense. I want the middle being multiplying by the number 1, meaning no frequency change. And so in order to make the middle of my sine graph be 1, all I need to do is go ahead and take this equation, add parentheses, and then add 1 to it, which will shift that middle from 0 to 1. And now it's shifting the frequency up and shifting it down. The next thing I'm going to need to do is actually change the amplitude. Because if I don't change the amplitude of this, what this is saying is when sine reaches its peak and its amplitude is just the plain old 1, 1 plus 1 is 2. That means I'm shifting the frequency up a whole octave. And then when I shift it down, it goes down even further. And so for me to better model just how gentle this pitch shifting effect might be, I'm going to change my amplitude to something much smaller, like 0.1. Now let's go ahead and see what that does to our graph. I went ahead and changed it to 0.3 just because it was a lot harder to actually visually see what was happening. But as soon as I changed it to 0.3, it's a lot easier to see that as I move to the right here, those peaks and those valleys are a little closer together. And as I move to the left, they look to be farther apart. And the closer together, the higher the frequency, the pitch is going up. And when they're farther apart to the left, the pitch is going down. Okay, finally, let's do a phase shift where we have a phase shift that is a delay, which means it takes the signal and delays it in time. To know how long in time we need to delay it, we need to know how long our delay is. Delays can range anywhere from 50, 100 milliseconds all the way up to over a full second. It turns out if you want to delay it by a fixed amount of time, you need to change your C to be equal to negative 343, whatever B is, times that, and then times your time in seconds. So if it's 300 milliseconds, that'd be 0.3 seconds. And so you can see here I've actually just added a slider here for time, so you can see as I shift the time back, the delay moves the signal to the right, meaning it's delayed backwards in time. You can do what I did here and change C to negative 343 BT, and then input as a slider your T and tell it your time. What is your delay time? That's just some examples of how to do amplitude, period, and phase shift changes based on the effect that you choose. In the next video, we'll do the exceeding level where we deal with a complex tone.